Hello, welcome. In this session, we look at this problem on simple harmonic motion. It says a particle of mass 2m is suspended from a fixed point O by a light elastic string of natural length 4L and modulus of elasticity 4mg. The particle is pulled down to a point A at a distance 10L below O and then released from rest. Show that it starts to move with simple harmonic motion of period 2 pi the root of 2L on G, and that the time that elapses before the string first becomes slack is 2 pi over 3 the root of 2L on G. Find also the height above A to which the particle rises. This is a question from the Cameroon GCE board for the mathematics paper 3. Okay, we begin with the diagram. The first part of the diagram is showing the string fixed at O, and the particle is attached to the string so that it hangs at equilibrium. So at the level E is the equilibrium position where the particle is hanging at rest, while the level N is the level of the natural length of the string, whose length was given as 4L. And the distance from N, the natural length, to the equilibrium position is denoted E, which stands for the equilibrium extension. So the particle is naturally supposed to pull down on the string while it rests at equilibrium. So we need that equilibrium extension in the calculation. Subsequently, we have to calculate that equilibrium extension using the fact that at equilibrium the tension is equal to the weight of the particle. Further, the question says the particle has been pulled down from the equilibrium position to a point A. So this is the level of A where the particle is now, and then released from rest. So we also need the further distance that is pulled from the equilibrium extension, which has been denoted in the diagram as D. It is also important in the calculation. Then the last part of the diagram is showing a general point where the particle is as it begins motion once it is released from rest, a point P where the particle is situated, and its displacement from the equilibrium position is x at that general point. Then we note that the direction of the acceleration is supposed to be the direction of increasing x. So it's pointing downwards because x is supposed to be increasing downwards. And so in order to calculate or to demonstrate that the motion is actually simple harmonic, we are going to apply Newton's second law in the direction of that acceleration. So briefly, that is the diagram that will help us in the calculation. We start straight away with the first part of the question, proving that the motion is simple harmonic and of period t equals 2 pi the root of 2L on G. Again, I bring the diagram. In order to do that calculation and prove the motion being simple harmonic, as I earlier said, we need to apply Newton's second law in the downward direction. But before doing that, we would first need to calculate the equilibrium extension. And so we begin by stating that at equilibrium position, the tension TE is equal to 2mg. The tension will be equal to the weight, as I already explained. But from Hooke's law, that equilibrium tension is supposed to be the modulus of elasticity times the equilibrium extension all over the natural length. The modulus of elasticity is given as 4mg, so times the equilibrium extension all over the natural length, which is given as 4L. So simplifying, we get that at equilibrium the tension is mge over L. If we now equate it to the weight, we have that mge over L equals 2m, the mass times the acceleration due to gravity, which gives the weight. And from here we can solve for E, the equilibrium extension, as 2L. Once we have E, then we can also calculate D, that distance from the equilibrium extension to A, where the particle has been pulled and reached. D plus E plus the natural length should give 10L, as the question specified, so that D should be 4L. And now we can apply Newton's second law at point P. This is where P is, and the acceleration is downwards. So Newton's second law would be that the resultant force downwards is equal to the mass times the acceleration. So the leading force downwards is the weight, and the opposing force is the tension at P acting vertically upwards. And so we have that 2mg minus the tension at P equals the mass times the acceleration. And it should be noted that the tension at P again is calculated using Hooke's law, whereby we have the modulus of elasticity times the total extension at P. At P, the extension from the natural length at the level of n there, we have first the equilibrium extension and then the distance x. So the total extension is E, the equilibrium extension, plus x. That's what we have here, all over the natural length, which is 4L, equals the mass times the acceleration. So we proceed to replace E, the natural length, E, the equilibrium extension, which was determined in the previous section as 2L, and then proceed to simplify the equation by distributing the denominator to have this, and then we cancel the m's in all the terms. Finally, the equation simplifies to x dot dot equals negative g all over 2lx, which clearly is identical to the equation or the standard equation of simple harmonic motion, whereby the angular speed omega equals the root of g over 2l, and the period can then be calculated from t equals 2 pi over omega, the angular speed, so that we have t equals 2 pi the root of 2l over g as required. In the next part of the question, we are required to prove that the time that elapses before the string first becomes slack is 2 pi all over 3 the root of 2l over g. Again, we start by looking at the diagram. The time that elapses before the string first becomes slack is simply the time the particle takes to move to the level of n. The string can only first become slack when the particle has reached the level of the natural length of the string. That is when it can become slack. And so, to calculate that time, we need to make use of the equation of the displacement of the particle, in which we would be needing the displacement of the particle at the level of n, which is 2L, because from E to N is the equilibrium extension, which is 2L, but in the real sense it is negative, because the particle has found itself on the opposite side of the equilibrium position. It was first down, and at the level of n it is now up above the equilibrium position. So that displacement of the particle from the equilibrium position at the level of n is supposed to be negative e being 2l, x would be negative 2l at the point n. So we have that the string first becomes slack at n, where x equals negative e, which is negative 2l. We also recall that the amplitude of motion is d, the maximum displacement from the equilibrium position. So, and it was determined in the previous part as 4l. From here, we now proceed to write down the equation of the displacement of the particle at time t, which is given by x equals a cos omega t. We are using a cos omega t for the displacement because the motion started away from the equilibrium position and is moving towards the equilibrium position. And so the displacement makes use of a cos omega t. If the motion was from the equilibrium position moving away to the extremes, then we'll be using x equals a sine omega t. So from here, a, we recall that a is 4l and at n, x is negative 2l, as already explained, because n is on the opposite side of the equilibrium position relative to where the particle started. And so replacing those parameters into the equation above, we have that negative 2l x equals the amplitude 4l cos omega, omega being the root of g over 2l, as what was obtained in the previous part, then times t. Now m is to make t the subject, so the root of g over 2l t equals cos inverse of negative half when you divide negative 2l by 4l. And so cos inverse of negative half being 120 degrees, we write it as 2 pi over 3 radians. And so making t the subject, we have that 2 pi over 3 divided by the root of g over 2l, which gives t as 2 pi over 3 the root of 2l over g as required. In the last part of the question, we are asked to find the height above A to which the particle rises. Again, the diagram is here and the particle starts from A, released from rest, and is moving upwards. So for it to rise above A, it would surely reach N with a certain speed different from 0, and so it has the tendency or the capacity to rise above n, and this time above n it will be moving solely under the influence of gravity. So we need to calculate the maximum height that the particle will reach above n, and to do that we would also need to calculate the speed with which the particle reached n. And so we have to note that if h is the maximum height the particle reaches above n, then the height above a, which the question is asking, can be denoted h, and h is given by d, the distance from a to the equilibrium position, plus e, the equilibrium extension, and then that maximum height risen above n under the influence of gravity. So h equals d plus e plus h, and we already know d and e, all of them in terms of L, where d is 4L plus 2L, the equilibrium extension, and so we need to determine h also in terms of L. In order to calculate h, we need to first find the speed of the particle as it reaches n, which would now serve as the initial speed with which the particle will begin to ascend above n into the air. And to calculate v, we make use of the equation v squared equals omega squared into a squared minus x squared, where v is the linear speed of the particle, omega is the angular speed, a is the amplitude, and x is the displacement from the equilibrium position. Now omega squared was determined in the previous part as g over 2l into the amplitude, which is 4l all squared, minus the displacement at n, which is negative 2l all squared. Expanding and simplifying, we have that v squared equals 6gl. It should be noted again that this 6gl is the square of the initial speed with which the particle will start rising into the air after going beyond n. And so we can calculate the maximum height reached using v squared equals u squared plus 2as, and the s now is the maximum height h. If we make it the subject, we have that v squared minus u squared all over 2a would give that maximum height. Now at maximum height, the velocity or the speed of the particle is 0. So we have 0 squared, which is 0 minus the initial speed, the square of the initial speed, which again we have noted that it is the speed with which the particle reached n, which we are just from calculating above. And so that u squared would be 6gl all over 2a, a being the acceleration due to gravity, and it's negative because the body is moving, or the particle is moving against gravity. And doing the calculation and simplifying, we have that the maximum height reached above n is 3l. Hence we can then calculate the maximum height reached above a as h equal d plus e plus h, which d is 4l and e is 2l. Then the h we are just from calculating is 3l. So the maximum height reached above a is 9l. And so this is all the solution to the question. Thanks for watching, and see you in the next video.